I'm here to share the ZVM on behalf of the openEuler community. And my topic is ZVM, Zephyr-based Virtual Machine. And let me have a brief introduction of myself. I'm a PhD student from Hunan University, and in the open source community work and openEuler Zephyr maintainer and president of the openAtom open source student association at Hunan Universities. At the same time, I'm Zephyr project and openEuler ZVM developer. And I'm here to share the ZVM and what's ZVM? ZVM is an open source embedded hypervisor based on the Zephyr RTOS. You may heard of the Zephyr RTOS. It's a popular open source embedded operation system in the Linux Foundation. And the ZVM is developed based on such excellent open source embedded operation systems. And why we talking about ZVM? The first is demand for virtualization in embedded scenario is increasing. Example, intelligent transportation systems maybe use a hypervisor to run multiple OS in one platform. And the second, there is a relative few hypervisors based on the real-time hypervisor. So it's maybe meaningful for someone to use it. And then for the student or the developer, they may need to learn the hypervisor to know how it works. The ZVM may be a simple sample to help them to understand how to design a simple hypervisor and how to use the simple hypervisor. And then we will talk about how to deploy the ZVM. Now we can deploy the ZVM on the virtual platform or a real hardware platform. Example for the ARM fixed virtual platform on the QEMU emulator. It's the virtual platform, and then we can deploy it on the developer board, like Rockchip RK3568 system chip. And if you are new to the ZVM, I recommend that you use the QEMU emulator because it's more simple than the others. The ZVM is maintaining the compatibility with the Zephyr origin build systems. It means that you can use the west command to build the ZVM just like build a Zephyr. And then you can use the QEMU emulator to start the ZVM. This is the start command. Maybe use the QEMU Arch64 emulator to start up ZVM. And finally, you can get a QEMU ZVM example. For example, ZVM host shell, and you can use this shell to create or to run in the virtual machine. And that is what to deployment the ZVM. And you may ask why we use the ZVM. In some embedded systems, it's needed to meet the practical deployment requirements of rich features OS and time constraints. For example, the intelligent control system in the car or intelligent industrial control system. And in such a system, they may need two types of OS. One is the rich feature OS for in the car, just like in the car, we can see it's an intelligent cockpit with data visualization and human machine interactions. And with another type is the real-time OS for intelligent driving, just like the traction control, power control, and other motor control. And these two of them can be considered as the twin starter coexistent systems, just like the figures. And the rich feature OS is as the main star, and the real-time OS is as the second star. Just give a example, like the main star may be openEuler, and the second step may be a QX for QX RTOS. So in such a mixed character system, they a single hardware platform and with multiple OS, multiple VMs, and with various applications for different functions. That is why we to develop such a embedded hypervisor. And then we introduce the framework, the ZVM. We can see in the picture that ZVM can divide it into 4 layers, include the hardware layers, hypervisor layers, guest OS layers, and the applications. First, for hardware layers, we support the NVA architecture CPU, including support the core device such as process, memory, and interrupt controller, and etc. For the virtualization layer, it's about the core virtualization extension models like the vCPU, vMemory, and vDevice. And for the volatile framework or other shared memory or other function. And ZVM reuse the Zephyr RTOS kernel OS, just like this, and reuse its Java modes and other function. And then in the guest kernel layers, it's we can use the ZVM to create multiple virtual machine like the Zephyr RTOS or openEuler or other Linux with ARM8 architectures. And the up layer is the application layers. We can run the real-time or non-real-time applications for the different function. And then we talk about the ZVM in openEuler embedded. You can see in this picture that the openEuler embedded will need embedded virtualization to boot several OS. And ZVM will as a part of an openEuler embedded ecosystems to provide some virtualization capability to run multiple OS. The ZVM, the main function of ZVM including the managing the virtualization resource. For example, managing the process resource or memory resource or the device resource. And then it can providing the API to the up layer VM, just like to apply to provide hardware access API for the service VM to control the real hardware. And then it's supporting multiple operating systems, including the openEuler embedded Ubuntu and Zephyr RTOS. And in the future, we are support the Android and free RTOS. And it is the ZVM in the openEuler embedded ecosystems. And in the future, we will try our best to merge the ZVM to the Zephyr mainstream, to merge into the Zephyr ecosystems to be a international community with a part of as a part of the Zephyr RTOS. And then we choose the features of ZVM, the technical features of ZVM. First is the system configurability. It supports flexible configuration of the ZVM, can switch between type 1 to type 2 hypervisor as needed. The second is the dynamic resource. It includes the dynamic memory allocation, dynamic device allocation when VM starts, and the adaptive task scheduling. And the third is the device virtualization. It includes the device pass-through and the device for virtualization and the parallel virtualizations with the volatile framework. And the fourth is the inter-VM communications. We support communication between VMs based on the Zephyr framework and the shared memory. And the fifth is the real-time features. We reuse the real-time performance of the Zephyr RTOS and to support some preemptive or deadline scheduling strategy. And the sixth is the edge-side inference. It's about support for Padlet. Edge-side AI inference framework supports like models like ResNet 50 and others. And then we just tell the detail of the technique of the ZVM. First is system configurations. It's about how we to configure the over ZVM. It's It's include two parts. First one is how to configure the VMs. And we use the device tree to individually to configure VM according to the description, device tree description file, just like this. And we use this, we can decide how many devices the VM can get and how many models they can get, or can pass some system info to the VM. And the second part is the kconfig systems, just like the Linux, and we can use the kconfig system to compare the ZVM itself. For example, to decide which subsystem will be built into the ZVM, and what's the VM function or other models can be built into the ZVM. And with these features, ZVM can switch from the type 1 and the type 2 hypervisor. For example, if it's the type 1 hypervisor, it means that few of the subsystem may be built into the ZVM itself. And if it's the type 2 hypervisor, it means that the most of the kernel service or other service may be built into over ZVM. And the second is the dynamic resource management. It can provide a flexible use of hardware resource. It also can divide to two parts. The first one is the device allocations. It means that ZVM can unify all the devices in the hardware board and to assign the device to the specific VM when the VM starts up. And then is the memory allocations. ZVM uses a double linked list maintain memory space for each VM, and ZVM will build the build the page table for each VM to translate the VM's virtual address to the physical address. And then ZVM also can provide different page table to different OS. Maybe a small page table for Zephyr VM or a bigger page table for Linux VM. And based on the Zephyr Hyper Memory Management, ZVM supports the quick, rapidly memory allocations. It makes the ZVM more easy to use. And then the device virtualizations. ZVM uses different virtualization methods for the different device type. For example, for the core device, just like the interrupt controller or clock controller or the PCIe bus controllers, we use the full virtualization method. Because if the improper access to such a core device may cause fatal error in the system. And then we support the parity virtualization device, just like a volatile block based on a volatile framework. And it's common in other virtualization systems, just like Linux KVM or Zen. And with the volatile framework, we can easily to add a volatile device to our system. And then is passed through device mode. It's based on the Zephyr's device mode. And with this device mode, we can initiate the device and lock the device to the idle device list when the system boots. And then when we want to start a VM, we will to instantiate the virtual device and to use the virtual device drive to allocate the virtual device to the VM. And when the VM want to access the device, ZVM will establish a MML map for each VM, so it can directly access the hardware and do not need to Cynic or other mechanism. And then for the interrupt management, ZVM handle the device interrupt through the driver's API and can redirect the device interrupt to the VM. And the first is inter-VM communications. It's with the VM communications, it can enhance resource sharing and collaboration between virtual machines. Just like a VM with Zephyr and a VM with openEuler can communicate with others. And with the FOSSASIA standard framework, we can implement the data sharing between the two VMs based on a shared memory, just like the memory load. And this memory load is to organize into a MVL tree for a quick search. And then this framework is highly portable and is suitable for multiple operating systems. Now it can be deployed in the Zephyr and the openEuler, and we can easily port it to the Ubuntu or other operating systems. And finally, with such a shared memory method, it supports real-time high-speed communication between VMs. And then is the real-time features. Real-time ZVM have a real-time assurance based on a Zephyr RTOS platform. You can see that it supports different scheduling queues, like a single list linked list, or a double linked list, or read block trees. And it also supports multiple scheduling strategy, like collaborative or preemptive priority, and earliest deadline first real-time scheduling. And because our ZVM is a lightweight kernel, so it has facility to real-time performance analysis or verifications. And finally is the edge-side interface. ZVM is supporting real-time inference on the edge side under the virtualization environment. It's because the Padlet and the TensorFlow are supported on the Zephyr RTOS VM. So when ZVM to boot Zephyr, it can to run a Padlet and the TensorFlow. And this it can meet the real-time requirements in the source-constrained embedded platform, and with such embedded hypervisors. With these features, it can expand the application domain of the Zephyr and make the Zephyr and VM more opportunity in the edge side, and it make the ecosystem more better. And this is our use case of ZVM, and it's a self-balanced car. And in this board, it's running two types of OS. One is the openEuler, and the other is the Zephyr RTOS. And the hardware is 4 links OK3568C developer board. It's based on the Rock chip RK3568 system chip. And the software is just described and is one ZVM and one Zephyr and with one Linux. And the Zephyr is the real-time control. It can achieve process control of self-balance, and it can be seen as the demo of a simple mixed corrective system. And finally is our open source works. First is the ZVM. ZVM is a project on the openEuler source communities, and you can, if you want to try ZVM, you can go to this link and to try to download the code to try the ZVM. The second is we are sharing our ZVM video in the Zephyr Developer Summit as Global Embedded Open Source Summit in 2023, and we make ZVM is competition project in computer system development capacity competition in China, and finally we a part of ZVM is merged into the Padlet Pad community project. And that's all. Thanks everyone, and also thanks to the opportunity provided by the openEuler and FOSSASIA.